Hi everyone. So today we are going to look at the concept of hydraulic diameter. So the first question is that why do we need this hydraulic diameter? Okay. So to answer this, let me take an example. So suppose this is a circular pipe. Okay. This is our circular pipe and the flow is going from left to right. Okay. So for this pipe, if we want to write the Reynolds number, we will write it as the Reynolds number is equal to density of the fluid into velocity of the fluid into diameter of this circular pipe, okay, divided by the dynamic viscosity, okay, mu. So now the question arises that how do we write the Reynolds number in case of a non-circular pipe? Okay, so uh, in case of non-circular pipe, we will just replace this diameter by the hydraulic diameter. So in case of a non-circular pipe, we will write the Reynolds number h density into velocity, and in place of diameter we will write it as hydraulic diameter, okay, dh divided by the dynamic viscosity. Okay, so this is the formula for the Reynolds number in case of a non-circular pipe. Okay, now the question is that what is this hydraulic diameter? Okay, so in the next slides we will see how to calculate this hydraulic diameter for different shapes. Okay, so let's go to the next slide. Now let's look at the first point. So it says that for flow through a non-circular pipe, the Reynolds number is based on the hydraulic diameter. This is what I explained in the previous slide. Okay, that for a non-circular pipe, the Reynolds number is based on the hydraulic diameter. Okay, now let's see what is hydraulic diameter. That how do we write the hydraulic diameter? So the hydraulic diameter is defined as dh, h for hydraulic. Okay, so dh is the hydraulic diameter and is equal to 4 times area of cross section. This is AC, area of cross section, and P is the weighted perimeter. Okay, so this is the formula for hydraulic diameter. Okay, now this is the area of cross section AC and this is the weighted perimeter. Okay, now the question is that what is this weighted perimeter? So let me take an example here. So suppose this is a square duct, okay, and the flow is going in this direction. Okay, the flow is going here like this. Okay, this is the frontal view. So, and suppose the pipe is fully filled with liquid. Okay, the pipe is fully filled with liquid. Okay, it is fully filled. The liquid touches all the sides. Okay, the liquid that is flowing inside the pipe or the duct touches all the 4 sides of the duct. Okay, so in this case, if you want to write the perimeter, the weighted perimeter, so suppose this is A, and since this is square, this will also be A, this will also be A, and this will also be A. Okay, so in this case the weighted perimeter will be the sum of all these 4 sides, because the liquid touches all the 4 sides. So the weighted perimeter will be P is equal to 4 times A. Okay, now let's take another example. So suppose this is another pipe. Okay, it has the lengths A, B. Okay, and the flow is going in this direction. This is like a rectangular duct. Okay, and the flow is in this direction. Okay, so suppose this is only partially filled. Okay, this is not fully filled, this is only partially filled. Okay, so suppose this is filled up to here. Okay, this is filled up to here only. So how do we write the weighted perimeter in this case? So let's see. Okay, so the liquid touches this side up to here only, this whole side, okay, and this side up to here. okay, this length only. So we will suppose this length of this pipe is A1, okay, and similarly on this side this length is A1. So in this case, if we want to write the weighted perimeter, we will we will write the weighted perimeter as P is equal to, look at the sides or the length of the sides at at which the liquid is in contact. So the liquid on the left hand side, the liquid is in contact with the length A1, okay. Look, the total length of the pipe of this side is A, okay, but the liquid is in contact with only this much length, and this much length we have taken as A1, okay. So we will take A1 plus this whole length, because the liquid is in contact with this whole length, that is B, and similarly on the right hand side the liquid is touching only the A1, so we write here as A1, okay. So this is the weighted perimeter for this case. So I think you have now understood the weighted perimeter concept. So let's now move on to the next slide. So now let's see that how do we write the hydraulic diameter for a circular tube. So suppose this is our circular tube, this is the inner part of this tube, and it has a diameter of D, and it has a circular cross section, okay. So look here, we have the hydraulic diameter formula as 4 into area of cross section divided by perimeter, okay. And for this case we have the area of cross section as pi d square by 4, because this shape is circular, so we have the area of cross section as the area of circle, and this is equal to pi d square divided by 4. Now the question is that how do we write the weighted perimeter. So for this case, assume that the fluid is flowing inside this tube, and it is fully, and this tube is fully filled, okay. This inner part is fully filled. So for this case the fluid is touching the entire circle, so the weighted perimeter will be pi d, because for a circle the perimeter is pi times d, okay. So for this case the weighted perimeter is pi d, okay. So we have the hydraulic diameter as 4 into area of cross section, this is the area of cross section, and this is the weighted perimeter, okay. Now see here, this pi cancels out, this 4 cancels with this 4, and the square cancels with this d. So we have the hydraulic diameter equal to the diameter of the tube. So for a circular tube the hydraulic diameter is equal to the diameter, okay. Now let's move on to the next slide. Okay, now let's see the hydraulic diameter for a square duct. So this is our square duct. So let me draw the full figure here. This is basically like this, okay. So the fluid is going in this direction, okay. Now assume that the pipe is fully filled, okay. This duct is fully filled, it is fully filled, okay. As you can see, the length of this square duct, the length of the side of this square duct is A, okay, and this is fully filled. So if we want to add the cross sectional area, so we will have the cross sectional area as this area, okay. So we can write it as A square, this is the area of A square, okay. So we have the cross sectional area as A square. Now what is the weighted perimeter in this case? So as we can see, the fluid touches all the 4 sides of the surface, okay. So the weighted perimeter will be the sum of all these 4 sides. This will be equal to 4A, 4 times A, okay. So we have the hydraulic diameter formula H, dH is equal to 4 times the cross sectional area divided by the weighted perimeter. So on cancelling, this will become A. So in case of square duct, the hydraulic diameter is equal to the size, the hydraulic diameter is equal to the length of the side, okay. So I hope this is clear. Now let's move on to the next slide. Now let's see the hydraulic diameter for a rectangular duct, okay. So this is a rectangular duct, so this is like this, the flow is going in this direction only as in the previous case. So as you can see, this is a rectangular duct. It has a length A and the breadth B. Okay, so for this case also the fluid is occupying the entire space. Okay, so if we want to write the wetted perimeter, it will be the perimeter of this inside a rectangle. Okay, so it will be 2 times of A plus B. That is, look here, it is 2 times of A plus B. This is the wetted perimeter. Okay, and if you want to write the cross sectional area, so look here, this is the rectangle. So if we want to write the cross sectional area, this will be AB. Okay, so we have the hydraulic diameter as 4 times of cross sectional area divided by the wetted perimeter. Okay, and on simplification, just divide it by 2. So we have the hydraulic diameter as 2 times of AB divided by A plus B. Okay, this is the hydraulic diameter for a rectangular duct. Okay, so I hope this is clear. Now let's go to the next slide. Okay, now let's see what is the hydraulic diameter for a channel. Okay, so as you can see here, this is the open channel. Okay, let me first draw the whole diagram. So the liquid is going in this direction. This blue line represents the level of the liquid, and this green line is for pipe. Okay, so the pipe is like this. Okay, so this is an open channel. Okay, now as you can see, this is not fully filled. Look at this part, the frontal part. As you can see, this is not fully filled. So in this case, suppose this length is A. Okay, this is written here, this length up to which the fluid is touching the sides is A. Okay, and this length on the bottom is B. So for this case, we can write the area of cross section as, this is A times B. So we can write the area of cross section as AB, and we can write the wetted perimeter as, so see here, the fluid is in contact with this part, and this part. Okay, so we can write the perimeter as A plus B plus the right part. Okay, this part. Okay, so A, so the total is 2 times of A, okay, plus B. So this is the wetted perimeter. Okay, so we have the hydraulic diameter as 4 times of the cross sectional area divided by the wetted perimeter. So this is the hydraulic diameter in case of a channel, open channel. Okay, so I hope this is clear now. So that's all. Thank you.